Hey everybody, so what I'm going to talk today is about how can we build the causality of the entire world. This task is actually the essence of everything we've been talking about AI. PsyCorp actually got $50 million in the 80s of trying to model everything humanity knows, but manually. Well, it didn't work, and we kind of went to the winter of AI, but many more models started developing at that time. Pearl was actually trying to develop a model that humans can model the different causalities starting from biology and different types of effects. At that point, he got the Turing Awards about that. But eventually, kind of AI stopped talking about the most basic aspects of causality and how the world works, just because it was really hard for everybody to model everything we know about the world. And instead, we started getting much more data all the time and went to statistical learning from data. And since then, if we look at the entire period of time, everything kind of looks the same, right? We have positive examples, we have negative examples. Sometimes it might be regression problems. And we've been developing much more and more algorithms trying to do exactly the same stuff. But what it can give you is understandings of the following form. We can actually giving a product that was sold in the past, just ask how many more times it's going to be sold. But what if I ask you a much harder question? What if I ask you, what's going to happen when this product, you raise the price and you sell it next to another product? What's going to happen now? If you don't have an understanding of causality, you cannot answer this type of problems. One of the biggest examples that was discussed in the past, and it was actually a true story in the 49, that people were discussing the fact that ice cream is causing polio. Think about those poor kids that had polio and were deprived of ice cream as well. Well, actually, it's a mere correlation. It was just happening in the same times that people were having ice creams. This disease has better times in the summer. So what we really understand is causality isn't a property of the data. The only way to understand real causality is to do some controlled experiment. The real way to do it is to live in the world and experience it, and based on that, to understand it. And what my main thing in the world is to understand is, can we mine everything humanity knows into a huge causality graph? And this causality graph will encapsulate inside everything that we know one causes another. Based on that, we can try to predict future events, we can predict the next breakthrough in medicine, we can predict who's going to buy what in economy. And what I'm going to show you is a few applications of building those type of causality graphs and simulators for different types of applications. So the first one is trying to take all this knowledge and predict any type of future events. For this, we're taking the entire New York Times archive since 1851. Afterwards, we're taking all Google searches for that, we're taking Twitter analysis, but basically it was taking a bunch of data, trying to build a machine learning algorithm that's going to look at pairs of cause and effect that's going to mine, try to abstract it with all the world knowledge, and make future prediction based on that. So the first part is actually understanding what an event is. And luckily enough, there's enough philosophers, including Kim and Schenck in '79, that were actually talking about the philosophy of an event. And I can summarize it pretty much in 3 points. The first one is 2 events should be comparable. You should know whether one is the same one or one is generalization of the other one. And you need the ability to reason from it. So what we were actually doing is taking text, like US Army builds a weapon warehouse in Kabul with the missiles, and trying to understand who did the action, in this case it's the US Army, what the action was done, the bombs, and weapon warehouse, what was bombed, the location is Kabul with missiles. With this type of understanding of a text into a much more structured form, we were able to understand who did the action, what it was done to, etc. The next phase would actually try to find clues in the text that talk about causality. Let's say somebody said this causes that, this happened because of that, and actually link it to a completely different structured event. In this case, 5 Afghan troops were killed. The way we were doing that were as I said, taking the New York Times archive and building different types of patterns to extract. Not all patterns can be very simple as because of or after. They actually need to have some kind of syntactic and semantic analysis into them. Afterwards, we're trying to use different types of augmentation of the data, including disambiguation of some of the words. But eventually, what we got is 300 million nodes and billions of edges based on 13 million news articles in total. But the problem is, let's say you have all these events. So now I have 2 events, and I can say whether they're similar or not. So let's say you have an earthquake in Australia. You look in your database. There was no earthquake in Australia. You don't give up. You find an earthquake in Turkey. How would you know that an earthquake in Turkey and an earthquake in Australia have something in common? How would you know that both of them are countries and that the consequences of both of those events might be similar in this event as well? So what we need for this is the ability to generalize event. In our case, we need to generalize both the objects, the people who did the action, who the action was done to, and including we would need to be able to generalize the action itself. So how will we do that? We can generalize things like the Russian Federation's in numerous ways. We can say it's next to China. It has a ruble. It stopped existing at one point. But how would we get all this knowledge about all these possible generalizations ever? For this, we go to human-labeled ontologies like the linked data. Linked data is a long-going project with hundreds of different data sets and billions of different facts. Some of them are pretty well known, like Wikipedia. Some of them are more structured form, like DBpedia. They have information about the genome data and including things about what we have in the supermarket. So we have some ability to generalize the different actors and what it was done on. But how do you generalize a verb? For this, again, we have so many different other ontologies like VerbNet. So Schenk was talking about the fact that we can generalize the entire language into pretty much 7 actions. Well, it didn't work. Instead, they were talking about around 200 different types of verbs or abstract verbs that you can generalize any type of verb. So in this case, you can say that hit is bang, bash, and kick are pretty much the same thing. So in order to generalize an event, right, you need to understand that, let's say, Baghdad and Kabul can be abstracted into a city using all these different ontologies. Strike and bomb are pretty much in the same class of different verbs. So now we have a similarity function. The moment you have a similarity function, you can apply many, many different clustering algorithms. So you can go through all these events happening in the past, look at their similarity, meaning how well can they be generalized to be the same event. And using, let's say here in this case, it's a Hierarchical clustering algorithm. And eventually what you get at the end is a huge forest of different abstractions of past events. The only trick is you cannot abstract everything into everything because, well, pretty much everything is abstracted to death, especially because of the corpus we've been using. So the thing that you want to do is, let's say you have different nodes in Wikipedia that can actually cause many things or can be generalized to many things. You want to actually decrease the similarity function based on that and different other heuristics. So we talked about how you generalize events. So let's say you have our earthquake in Australia. You look, and after the earthquake in Turkey, which is very similar in our case, Red Cross help was sent to Ankara. We all know that Red Cross help will not be sent to Ankara for an earthquake in Australia. It will be sent to? Well, yeah, kind of Canberra, right? Kind of the capital of. So what you need to do is kind of learn the different functions of how to augment the prediction or the effect of the cause happening. You cannot just output whatever happened in the past. You actually need to make it much more relevant to what's going on right now. But how would you do that? So luckily enough, at that point, let's say we have the same example of the US Army that's bombing and the 5 Afghan troops. What the algorithm is trying to find is this function that we're trying to apply. So at the beginning, we were talking about simple function like capital. In this case, you want to say that Kabul is the country of Afghanistan, the nationality of Afghan, and it's the attribute of the troops. So next time, we're going to have another army bombing, another weapon warehouse. You just need to go through the same path and say, hey, what is the country of what was bombed? What is their nationality, et cetera? And this is where the people are going to die. For that, what we're doing is looking at the same linked data structure. So they have different edges. Those different edges are actually giving you the labels of how you can abstract in a different way. Think about different label edges that you have in Wikipedia, so in a very similar form here. So in this case, the function is exactly the one mentioned here. So what I was describing right now is a way of taking all this like news, 30 million different articles, building a huge causality graph. But how do you use this causality graph to predict new future news events? So what we would do, we take a new event, look at our entire graph, go from the most abstract thing that can happen, and find the most similar things that look to it. And then we would apply the function on it. So let me give you a real example outputted by the system. So while I was working on this kind of stuff, I was working with a lot of different medical organizations. Some of them were really interested in the different Ebola ones. And what was really interesting, there's two types of Ebola viruses. One of them is coming from Zaire. And what the system found out is that, well, it's all because of greed. So if you have a volcano eruption or some kind of natural reaction, you're going to have people going for diamonds and gold. The system knew that when you look for diamonds and gold, that's going to happen deforestation. It actually read in some different medical articles that it was also mining that deforestation causes animal migration. We know that a bat is a type of animal. So it saw in the past that there wasn't a lot of Ebola outbreaks in humans, but there were dozens in animals. In all those cases, they all had the same things. Somebody ate a bat. So the system actually said that Ebola is actually going to happen in those areas as well. And think how complicated this going through the different edges and links in the graph is, especially without very few world knowledge around that. And this is pretty awesome. But we also had different types of much more easier predictions. So for example, you have a volcano eruption and thousands of people flee from Congo. We actually were trying to compare it to what people were saying. I think my favorite one, we were saying that a professor from Tehran University is killed by bombing, and we're asking people, what do you think is going to happen in the system? So when I was asking students in the Technion, they said that an academic position is now open. This is why we stopped using students for those experiments. Instead, what the Mechanical Turks were saying is that Islamist group would, that Tehran students will remember slain professor in memorial service. And what the system said is, there's going to be a funeral. Okay, actually, if you go in the newspaper, there was a funeral, but it's not interesting. It's not surprising. And which was actually pretty much disappointing for me is that besides, let's say, like different chains, like long chains, like the Ebola ones, the system is actually behaving like a 5-year-old. And the reason for that is actually very simple if you think about it. What the system was looking for is what humanity already knows about causality. It was looking for things like A causes B and kind of trying to generalize them. Nothing more, or connect them in different chain lines. This is not enough. So I know that correlation is not causation, but what's going to happen if we unite them? Can we find out things that people don't know yet? So the next thing that we started doing is trying to add more and more dynamics into our system and try to find correlations and add to that different causation changes as well. At that time, I was working at Microsoft Research, and we're really interested to predict malaria, cholera, etc. And one of the systems we were actually trying to really focus it to predict different disease outbreaks. So in 2006, there was a big drought in Africa, and I think a couple of years later, there was a big storm causing a cholera. But this is based on very few cases. But what if I told you that in Bangladesh, since '82, they had, I think, 90 significant cases of cholera. All of them had exactly the same pattern as I said. You have a drought, 2 years later, then you have storms, 2 weeks later you have cholera. So for example, here you have again the cholera outbreak. So for that, what we started doing is trying to take event chains that happen together. Very similar to the work that Daphne was presenting, we're trying to understand that, for example, all this storyline is actually talking about the same thing in a coherent way. Then using this types of event chains, we're trying to mine words that tend to happen temporally one after another. So for example, in this case, you have Cuba, drought, then a probability of storm 2 years later, and what's the probability given all of that you're going to have a cholera outbreak. The main problem in this type of data is that if you look at the past, given Cuba the cholera in Havana, never appeared in the news archive. So what we really want to do is, again, use the same notion of abstraction. What if instead of Cuba and Havana, we would say, hey, how many times did we have exactly this pattern in places with this population density, with this area of total, et cetera? Or we try to abstract it in a different way. Let's say, how many times did it happen in social states or island countries? Now notice again that you have Cuba and Havana. You need to understand that there's a function that you apply, Cuba and then the capital. So when you try and measure those probabilities, you again need to learn these different functions that you need to learn the statistics about them. So I'll show you this exact chain and how the system learned it. So it knew that cholera is caused by storms. It's not a big revolution. Everybody pretty knew that cholera is a waterborne disease, so it's not that surprising. And what the system found out is that if you have a drought 2 years later, the probability of these chains is much, much higher. And this is based on, I think, 6 cases in Angola, and I think a few dozens from Bangladesh. But what's in common between Angola and Bangladesh? So we again go to Wikipedia and the linked data sets. So it can be many things. It can be the area population, it can be the GDP, etc. So what the algorithm found out is that only 2 things actually matter. And this is the GDP. Whoa, poor countries have diseases, right? Not a big surprise. But what was a really big surprise is the percent of water. As I said, that cholera is a waterborne disease. So we do expect if you have a lot of water, you're going to have cholera. And what we found out is actually the exact opposite. If you don't have a lot of water, the probability of cholera is much higher. And the reason for that is that cholera is treated actually very easily. 100,000 people die from cholera every year, but you can drop mortality rate from 50% to less than 1% if you just get clean water in time. So what we think is that in places where they didn't have the clean water in time, this is what caused it. So I think about all this system as a hypothesis generation system. It actually looked at the past and find this interesting correlation/causation. And now based on that, we understood that there's some kind of link between cholera and weather data. So we started getting sensor data and weather data. And based on that, predict cholera with very high precision in a range. We didn't need 2 years. We only need a really good range of 3 to 4 months. When we started experimenting with the system, we were trying to predict, based on everything happening from 86 till 97, everything that's going to happen in 2000. And what we find out is actually that we have things that we're really good at predicting. We're really good at predicting death. Well, everybody's asking me, why is my system so gloomy? Why is it only predicting death? Well, it's trained on the news, right? Nobody's ever saying awesome stuff on the news. And really good in predicting riots and some forms of diseases. So there's still a lot of things to do. It was that good at predicting death that it was actually telling you how many people are gonna die in those areas. And not only that, had really nice alert time. At that time, I was working at Microsoft. I came back to Israel, and I was working with a lot of economists. They said, well, some of them were Nobel Prize winners, and they said, well, this is a very interesting system, but how do you make money out of it? Right? So you predict this disease, you predicted that disease. Maybe instead of that, you should predict the stock. And I think the best thing, the answer that the computer scientists were trying to say that, well, you got Nobel Prize for one hypothesis, we're going to build a system that thinks about thousands of seconds, eventually we're going to have one really good one. So I started experimenting with the system, but in a more economical setting. I was trying to predict the most important thing at that time is the iPad prices, at least to me. And what the system found out is that iPad price is going to go up very soon. And the reason for that is a tsunami in Japan, which is very intriguing. Tsunami in Japan, my iPad in the States, well, what's the connection? So it turned out that the tsunami in Japan in the past hurts factories. The system actually read that some of those factories are supplying different materials to another factory in China. Those ones are actually producing the iPads, and the system saw that in the past when you had a shortage of something, prices started going up. And this is very interesting. By the way, the prices didn't go up. But I just like the inference part of the system, and that it can actually understand things about the macroeconomic world that we have. But something was missing. In order to predict real things about economy, you cannot just use general news and what's going to happen between countries or the different prices. You really need to go deeper and understand microeconomy for that. So what we started doing is going to companies and saying, hey, just give us your internal data. We're going to augment it with all the data that we're going to crawl from the world, all this like macroeconomic graph that we have. And what we were trying to build and unite the macro and microeconomic modeling. So we had models trying to predict from customers' data what's the probability of different interactions happening between them and other companies. In addition to that, the different things that are happening in the world, and based on that, trying to predict what's going to happen with their business, how much money they're going to make, where they should focus, etc. And this is the company I started called SalesPredict. But every time I start doing those stuff, I'm thinking, well, I didn't start that because of money. I started money just because somebody told me, hey, you have all this awesome system, what can you do to make money out of it? And one of the things I'm mostly intrigued about is how can you use this huge hypothesis generation system to make breakthroughs in medicine? So at the same time, I was approached by several hospitals and HMOs, and I started getting data around yearly checkups of people since the 70s. For each one of them, we can know whether they're smoking, their different blood tests every year. Clearly, has data of around 4 million people. I think it's the second biggest data set in the world. Also got information about from Maccabi, one of the biggest HMOs in Israel as well. All of them have everything we have to know about medicine in Israel and people who are doing all this tests, and we had very interesting prediction problems, predicting cancer, predicting hypertension, diabetes, etc. The main problem in all the things we're trying to predict, and I'll give you an example, is we're trying to predict pneumonia in hospitals. So what we found out is that, and this is a famous problem around that, is that if somebody has asthma, the probability of having pneumonia in the hospital is almost zero. I came with this awesome non-intuitive insight to the doctors, which kind of found it funny, because what they said is that, well, of course, we know that asthma people always get pneumonia, so we just move them to the ICU in 2 seconds, right? So we treat them right away. This is not a real one. And this is where I started thinking, remember we had all this causality in the 80s and the beginning of the 90s, and AI stopped doing causality because it was hard, and then we moved to all this like machine learning and data mining and data-driven approaches. What's going to happen if we unite them? Because every time I was making any type of predictions in medicine, I always needed a doctor. The doctor would always tell me, no, this doesn't make sense. This is something else. And at one point I was thinking, well, he couldn't have read all those books and model all causality and all the biological processes. We don't have a body simulator. And this is when I thought, well, why not build a body simulator from text? So the concept would be taking information, so this is just Wikipedia, just because it's a nice picture, but you can take it from any biology book and read the process you have here about insulin, and then see that high blood sugar level is causing a transfer of insulin to beta cells. Now, if you're going to run a simulation on it, it's like, hey, what's going to happen if I'm going to add more insulin? What's going to happen if I add less? And then a lot of the correlations that we find in the data can actually be verified with the causality of the processes that we mine from text. And this is a real example of what our system is already doing. So it's taking very complicated sentences of what insulin causes, and says that the first event of conversion has to happen before the forcing, has to happen before the taking of glucose from the blood to the transporter in order to cause the decrease of blood sugar. And what we were doing in that way, we're pretty much building several classifiers. Each one knows for each event their arguments, and then a different ILP problem trying to predict the different relations between the different events happening in the same time. And the way I envision this system is a combination of both a system that mines all the data, all the millions of data that the HMOs and hospitals have of what doctors don't know, which are correlations, and giving them an option to actually simulate some of those correlations and have the experience with the world that any causality network actually needs. And with that, I'm going to finish and tell you that this is where I see the future of AI, trying to understand how we take everything that was the spring of AI in the 70s, the 80s, that became the winter, which we already forgot, and uniting it with all the approaches that we have today, which are the data-driven approaches. Thank you very much.